Hello, everyone. Welcome once again to the One World Combinatorics on Words seminar. So our speaker today is Dan Rust from the Open University, and he's going to speak to us about random substitutions.
Okay, great. Thank you, Narad, and thank you, Manon, for inviting me to present in this seminar. I've been attending now for, what is it, just over a year, and I'm always interested with the talks that happen in this seminar, so it's great that I've got the opportunity now to share some of the work that I've been doing. So first of all, my screen is over here, so I won't actually be looking in the camera when I'm speaking, so hopefully that's okay with everyone. Okay, so I'm going to be talking about today random substitutions. I think most of you are probably familiar with substitutions. So really, the interesting point about this talk will be what random means in this setting. So first of all, let's just set up some, well, let's give a quick summary first. So random substitutions, it's a bit like a substitution, except every time you substitute a letter, you flip a coin. And then depending on the outcome, you substitute either one way or another, or maybe have multiple options. We'll get into the details in a second. Their systematic study, say from the point of view of topological dynamics, which is the area that I tend to work in, started in 2016. And so because it's still really new, there are still lots of open questions. And really, it'd be nice if there were more people working in this area to tackle some of these questions. So hopefully advertising today can interest some of you. Okay, so as with normal substitutions, classical substitutions, with random substitutions, you want to look at a language that you build from a process. And that really is done in a very similar way to how it works for substitution. So I hope that the way that the language is built will feel really familiar. And because of that, it means that they lie somewhere between classical deterministic substitutions, which have long range order, and then maybe like shifts of finite type where you have local disorder. And we'll see that cropping up as entropy later. And just in case some of you are familiar with other terms, these also appear in many other guises. So they have been called in the past multi-substitutions or set-valued substitutions, or stochastic substitutions, or zero-L systems in the formal language community. And in terms of some of the aspects that have recently been explored, here are just a few of them. But today I want to talk about these two in particular. So the complexity function or the entropy, because they're both linked. And if I have time, I'll also speak about periodicity. But obviously, I'm happy to discuss any of the other aspects after the talk if maybe someone's interested in the automorphism groups or the diffraction, whatever. Okay, so let's look at some notation just to set us up. So this will all be very familiar. For me, A is a finite alphabet on D letters normally, and I'll label them A1 up to AD. A plus is the set of finite words over our alphabet. And if I put A star, that just means I'm also including the empty word. A to the Z is the full shift over our alphabet. So this is the space of all bi-infinite sequences over our alphabet. And on this compact space, there is a left shift map acting. So we call it sigma acting on A to the Z. And it just moves everything one place to the left. So it maps xi to xi plus 1. And if I call something x a subshift, that means it's a closed shift invariant subspace of our full shift. And just a bit of notation, if I write U triangle W, that means that U is a subword or a factor of W, where W can either be a finite word itself, or it could be an infinite or bi-infinite word. So just to get us warmed up, what is a substitution? Well, substitution is just a map which sends letters in our alphabet to non-empty words over our alphabet. And then for a substitution, we can build its language where we just take high powers of our substitution on a letter and look at all of the words which can appear as subwords of that. And then we include all of those subwords in our language. Okay, and then from that we can build a subshift, which is just all of those bi-infinite sequences where all of the subwords of that bi-infinite sequence appear in our language. So given the setup, what are some properties? So some basic properties of this subshift. It's a Cantor set. It has a linear complexity function. So by complexity, I mean the number of legal words, the number of words in our language of a particular length. It's normally aperiodic, minimal in the sense that it's only closed invariant subspaces itself, and it's uniquely ergodic. And these properties hold whenever our substitution theta is primitive and recognizable. And I'll give the definitions of these in a second. By the way, please feel free to interrupt if there are any questions if I'm going too fast. Okay, so to a substitution, normally one of the first things you want to look at and one of the most important tools is the Abelianization of the substitution. So the Abelianization is a matrix M theta, and the ijth or the mijth entry of that matrix is just the number of times that the letter aj appears in the word theta of ai. Okay, so here's an example. So this is the period doubling substitution. It maps A to the word AB, and it maps B to the word AA. And so that means that our matrix, well, the first column is the number of times that each of the letters appears in theta of A. So there is one occurrence of A in theta of A and one occurrence of B in theta of A. And then the second column is the number of times that each of the letters appears in theta of B. So we have 2 occurrences of A and no occurrences of B. Okay, and just to note, this matrix, it has 2 eigenvalues. So it has the largest eigenvalue 2, and then a second eigenvalue -1. And it has a right eigenvector. Here I've normalized so that the entries sum to 1. And this eigenvector is associated to the largest eigenvalue, so to 2. So here we have the eigenvector 2/3 and 1/3. Why is that important? Well, first of all, notice that this matrix M, it's what's called primitive. So if you take a large enough power of the matrix, then eventually all of the entries are positive. So in this case, if we take the second power of the matrix, if we take it square, then all of the entries become positive. And in that case, we call the matrix primitive. And then we also say that the substitution itself is primitive if that occurs. Whenever you have this, then the Perron-Frobenius theorem applies. And so that says that we have a largest real simple eigenvalue. And so we normally write lambda PF for this, or I'll just use lambda. And it's a real number. It's simple in the sense that it has a single positive eigenvector associated to it. And all of the other eigenvectors of the matrix are bounded strictly above by this eigenvalue in modulus. And I should say it's always positive as well. Okay, and what does the right eigenvector of this matrix tell us? Well, it encodes the frequencies of letters in our subshift. So if we take one of the elements of our subshift, one of these bi-infinite sequences, and we ask what is the frequency of the letter A? Well, for instance, with the period doubling substitution, the corresponding entry of the right eigenvector is 2/3. So that should say that A occurs roughly 2/3 of the time in any bi-infinite sequence in our subshift. And similarly, B would have 1/3 frequency. Okay, so what's the complexity function? Well, I'm just going to be talking about substitutions here, so I'll just stick to that setting. So for me, first of all, Ln is just the set of legal words which have length n. And then the complexity function, well, this is a function which takes natural numbers and maps them to natural numbers. And in particular, it tells you how many words of length n there are in the language. So normal questions that we might want to ask about this are, first of all, is there a strict formula that we give for the complexity function? Normally, you can't do that, but you can at least say what is the behavior of the function? What's the growth rate? And so for us, we're going to be looking at the exponential growth rate. So we normalize that by taking the logarithm and then dividing by the length that we're looking at. And so the exponential growth rate of the complexity function tells us what's called the topological entropy of our subshift. And this is a dynamical invariant of our subshift. So when we're just looking at substitutions, so if theta is just a deterministic primitive substitution, then it means that the complexity function actually always behaves linearly. It's always bounded by some linear function. And that means that if you take the logarithm and then divide by n, you're just going to end up with 0. So this has no exponential growth rate. In some sense, it's very well behaved. There's not much going on. That's going to change when we move to random substitutions in a second. Okay, so keeping this in mind, let's now talk about periodicity. This is normally maybe one of the other ways that you think about how complicated is my function. Is it periodic? Is it close to periodic? And at least for deterministic substitutions, this is essentially a settled question now. So a substitution theta, I should have written, I think, primitive somewhere. Oh, no, that comes later. So sorry. A substitution is called recognizable if for every element in its subshift, there is another unique element y and some unique shift factor I, such that if we shift by I to the right, then that is exactly the substitution of y. So what does that mean? It just means that every element out of subshift has a unique decomposition into inflation words. And if we were to code by those inflation words, that coding would itself be an element of the subshift. So it would be legal. And why am I introducing this definition? It's because of this famous theorem of Mosse from 92, which says that if our substitution theta is primitive, then we have this correspondence here that the substitution is recognizable if and only if its subshift is aperiodic. Okay, so periodicity corresponds to not being recognizable, and aperiodicity corresponds to recognizability. In general, the left to right implication of this theorem is rather easy, so it's just a few lines. The right to left implication is decidedly more difficult, and that's why this is such a celebrated theorem of Mosse. I should say that this theorem has now been generalized in any number of directions, and it's still causing a lot of research to occur. Okay, so that's periodicity for deterministic substitutions. Now let's move to random substitutions, and we'll try and put both the complexity function and periodicity into this new context. So what's the slogan for random substitutions first? Well, it's that letters have choices for how they're substituted. So I'll just give a definition by an example because it's probably the easiest way. So here is what's called the random period doubling substitution. And the rule for this random substitution is that A can either be mapped to AB or BA, right? Before we just had A could be mapped to AB. Now we have this second choice, BA. And then B, well, actually, we only have one choice here. So B can only get mapped to AA. And the important point that I want to emphasize is that these choices that we have are independent for each appearance of a letter. So whereas for S-adic substitutions, you pick a substitution and then you apply that same substitution to each letter in your word, here we have more choice. So every letter in our word can independently be acted upon by this random substitution. So here's a typical sequence of the substitution being applied repetitively. So we maybe start with the letter A, and then we go, okay, what can A get mapped to? Well, one choice is that A could get mapped to AB. We could have picked BA here, but let's go for AB. Now we substitute again. Well, okay, maybe this A gets mapped to BA now, and then B, where it has no choice, it has to get mapped to AA. And now things get interesting because we have 3 occurrences of A in this word, and each of these A's can themselves be independently substituted. So in this iteration, well, okay, B has no choice, it has to go to AA. But then these 3 A's, we go, okay, AB, BA, BA, and each of those were independent. And so we can continue and we get a longer and longer word. So even though here I've mapped things out linearly, really think of this as a kind of branching process, right? Each of these appearances of a letter which has multiple images corresponds to new branches in our tree. Okay, so given this, how do we build the language for our random substitution? Well, it's essentially the same as with deterministic substitution. So we take a high power of our random substitution. Remember now, this is a set of words, right? For each independent choice, we get a new word in our set. So this will be a large set of words. We then look at the words which appear in there and look at the subwords, which can occur as subwords of one of these elements inside this set. So this language, you can probably tell, is going to be a lot bigger than for deterministic substitutions. And then we build our subshift in exactly the same way as for deterministic substitutions. We just look at all of the bi-infinite elements of our full shift, such that all of the subwords of that element, of that bi-infinite sequence, appear inside the language. Okay, hopefully that's okay with everyone. So let's really explicitly write out some of these sets just to show how quickly things explode. So again, we're just looking at the random period doubling substitution here. So first of all, we have two choices for A, AB or BA. If we look at the second iteration, well, okay, each of these A's will give us two choices. So we should have 4 words appearing, and we do. So here, these 2 words come from the first image. These 2 words come from the second image. And then if we apply the random substitution again, well, now each of these 3 A's appearing in each of these words corresponds to themselves 2 images. So we should have 8 images of each of these words. And that's exactly what we get here. So these 8 come from the first word, these 8 come from the second, and so on. So things are exploding quite quickly. So before I get into some definitions about, for instance, complexity and periodicity, I just want to introduce a main assumption, which simplifies things quite a bit, but is still complicated enough that it gives us something to work with. So for me, the Abelianization function, psi, of a word is just the one which tells you how many of each type of letter appear in the word. And then we say a random substitution is compatible if in this set of images for a letter, for any 2 words inside that set of images, they have the same Abelianization. So that's just saying that our random substitution, even though it may have multiple choices for a letter, at least the number of each type of letter in those images isn't dependent on how we substitute. So why is this useful? Well, first of all, it means that the matrix associated with our substitution makes sense, right? We don't have any, probabilities involved or anything. And then that means that we can define primitivity. So we would say that our random substitution theta is primitive if the corresponding matrix is primitive. And that means that actually letter frequencies do exist now. So they exist uniformly. So every element of our subshift has letter frequencies, and they are independent of the element that we choose. And again, these are encoded by the right eigenvector of the matrix associated to our substitution. I just want to point out, though, that even though letter frequencies do exist uniformly, word frequencies in general do not exist. So there will be elements in our subshift which do not have a well-defined word frequency for words of length 2 or longer.
Dan, may I ask
Hi.
something? Hi. Is it to have a compatible substitution? Is it enough that the set of images of each letter in the substitution, those are they have the same Abelianization in each word, each image in. Okay, you take the images of A, each of them must have the same Abelianization. But is it possible to have some example where maybe not all of them have the same Abelianization, but you could eventually get something that is compatible?
I think it's possible that a substitution itself can't be is not compatible, but some power is. I think that's what you're
Okay, yeah.
asking, right?
Yes, I think so. Yeah.
Is that true? Maybe that's not the case. I'm sure I could cook up an example if one existed. Let's put it like that.
Yeah, okay. Right.
Thanks,
Thank you.
Okay, so let's look at some examples just to clarify that definition. So here's again the random period doubling substitution. So A, if we look, each of the images has a single occurrence of A and a single occurrence of B, and B just has a single image. So this is a compatible substitution. And so that means that the matrix exists, and it's actually the same matrix as the abelianization of the deterministic period doubling substitution. And you'll notice that if we take the square of this matrix, then all of the entries are positive again. And so this is a primitive matrix and therefore a primitive random substitution. Maybe a slightly more exotic example, just to really land it home. So here we have 3 letters in our alphabet. A has 2 images, but you'll notice that each of the images has a single A, 4 Bs, and a single C. And then B has 3 images. Each of them has 2 A's and 1 C, no B's. And C just has a single image. So again, this is a compatible substitution because the abelianizations are consistent. So that means we can define the matrix. Here's the matrix for this random substitution. And you'll notice that if you take the cube of this matrix, then all the entries are positive. And so this random substitution is also primitive. Okay, so what are some basic results for primitive random substitutions? So this was some work with Timo Spindler from Bielefeld in 2018. And we just really wanted to say, we wanted to ask what is some of the basic stuff that we can say when we just have this really mild primitivity condition, not much else. So if you have a primitive random substitution, then the subshift is either a Cantor set or it's finite. You either have no periodic points, so the subshift is aperiodic, or if you do have periodic points, then actually they have to be dense inside the subshift. So you have this dichotomy. You will have uncountably many minimal components. So that's very different to the deterministic setting where the subshift itself was minimal. Almost all orbits are dense. So in particular, we have topological transitivity. But by almost all, I'll just kind of sweep that under the rug, but it's related to this last entry here, talking about an invariant probability measure. We have positive topological entropy, but essentially almost always that there's a very small condition which ensures this. And yeah, Golka and Spindler last year, that they showed that there is this canonical measure where the measure is associated to a particular choice of probabilities for the images of letters. And from that choice of probabilities, you get this measure, which they showed was actually an ergodic measure. And in some sense, this measure is kind of the natural choice. So if you really do put a probability to your coin flip, then you want to know, okay, what's the frequency, say, of an A in one of our words? Well, the frequency would be coming from this probability measure that you're putting on your subshift. Okay. So let's talk again now about recognizability, because in the deterministic setting, it's essentially sorted, right? You're recognizable if and only if the subshift is aperiodic. Here, things are slightly different. So the definition of recognizability is essentially the same. So your random substitution is recognizable if for every element in your subshift, there is a unique pre-image, Y, and a unique shift associated to that pre-image. So that if we shift by X, by this I to the right, then it lands inside the image of Y under the random substitution. Notice before that we had an equal sign here because for a deterministic substitution, Y has exactly 1 image. Obviously here, we have a random substitution, so actually Y has infinitely many images under the random substitution. We're just asking that it is a pre-image, not that it's the only pre-image. sorry, not that it's the only image of the pre-image. So given this definition, we can at least show the easy direction of Mosse's result. So it is true that if our random substitution is recognizable, then our subshift is aperiodic. So what about the converse? Well, in fact, the converse fails really quite badly. So even if we take what some might consider one of the most basic examples of random substitution, the random Fibonacci substitution, which is given by A goes to AB or BA, and B goes to A, then this fails, the converse of this theorem up here. So notice we have irrational letter frequencies because this is a compatible primitive substitution. So letter frequencies still exist uniformly, and they're irrationally related, just like in the deterministic case, right? A has frequency 1 over the golden ratio, B has frequency 1 over the golden ratio squared. So they're related by a golden ratio to each other. So that means there can be no periodic points in the subshift. But this random substitution is not recognizable, even if we take the fixed point of the usual deterministic Fibonacci substitution, right? That obviously lives inside our subshift. It just means we've applied the same image to each of our A's. So that's in our subshift, but actually it has two, or I should say at least two pre-images, at least two decompositions into inflation words. One where you just decompose by looking, well, it is its own pre-image, right? If we decompose into A, B, and A, but we could also equally decompose into B, A, and A. And that also gives some other way of encoding our element as a concatenation of inflation words. And this is because for Fibonacci and reflected Fibonacci, they actually have the same language. This is kind of atypical, I guess, but for random Fibonacci, it has strong palindromic properties. So actually you do get it in this case. So, okay, that means that our converse isn't going to happen. So in particular, that means, well, you either look at it in two ways, right? Either you're sad because you don't have this nice theorem, or you're happy because now there's something hard to study, right? Whereas in deterministic, for deterministic substitutions, this is kind of settled and quite easy. For random substitutions, this is still a very murky area. We don't understand periodicity very well at the moment. And if I have time, I'll get back to periodicity later. Okay, so what about complexity, the complexity function and entropy for random substitutions? Well, just remember, so for a subshift, the topological entropy, h top, is just the exponential growth rate of our complexity function, right? So we renormalize by the logarithm and divide by n, look at the limit as this goes to infinity, and that gives us some real number. I should say this limit always exists. Okay, well, we at least know that we can bound this term below by the following quantity. Instead of just looking at all words in the language, how about we just look at some large power of the substitution applied to a letter and collect all of those possible images into one set? How many of those are there, and what's the exponential growth rate of that, right? So here, by these bars, they just mean that's the length of a word inside this set of words. Okay, so this gives us some obvious bound, and the hope, right, is that actually this bound is the same as the topological entropy. Even though we're looking at a smaller subset, its exponential growth rate is still the correct growth rate for us. Okay, so let's try and estimate some of the terms in this right-hand side. So first of all, notice that because of the Perron-Frobenius theorem, if we wanted to know how many times AJ occurs in some high iterate of the random substitution applied to the letter AI, well, that's just the same as applying the matrix K times to the ith identity vector, and then looking at the jth entry of that corresponding vector that we get out from that. By Perron-Frobenius theory, well, this is a primitive matrix, so some large power roughly looks like lambda to the k, where lambda's the eigenvalue, times the right eigenvector and the left eigenvector, and again, EI. Well, okay, you follow through some of the algebra and you end up just looking at the jth entry of the right eigenvector, the ith entry of the left eigenvector, times lambda to the k. Okay, so there are roughly lambda to the k times some constant appearances of aj in the kth iterate of the substitution applied to ai. And the constant is just dependent on the I and the j that you're looking at. Well, if we sum over all of the aj, then that's actually just going to tell us the length of this word, right? So the length of this word is then, well, okay, we've normalized the right eigenvector so that the entries sum to 1. So if we sum over that vector, then we just get li times lambda to the k. So the length of our words, right, this bottom term here is growing roughly like lambda to the k, which is what we would expect. That's exactly how things work in deterministic substitutions as well. And I should say this all comes from both compatibility and primitivity. So we need both of these assumptions here. Okay, how about the other term? How many words are in this set? Okay, so we want to know how many words are in the kth iterate of our round substitution applied to the letter AI. Well, if we take one step back, for each of the letters inside the previous, the pre-image, right? So theta to the k minus 1 of AI, then we first look at how many occurrences of each letter there are. So there are this many occurrences of aj in that word. And then we look at, okay, how many images does aj have under one application of the round substitution, right? So this big product here is telling us, is relating the number of words in this set to the number of words in this set. And if we iterate this, we go all the way back to just single letters, then we get some big product, which looks like this term here. So it's the number of images of a single aj times the number of appearances of aj inside the k minus s iterate of the round substitution. And then we take the product over all s. So in general, this is a very big number, which I'm sure you could guess. Okay, so I'll just put those three estimates up here so that we don't lose track of them. So let's put all of this together. So we want to estimate this term here. So 1 over the length of a higher iterate of our substitution applied to a letter times the logarithm of the number of words we get in some large power of the substitution applied to the letter AI. Well, okay, you follow through the algebra a little bit, you throw in all of our estimates, you then pass the log through, you then get a geometric series here. So if you follow that through, you end up in the limit getting a term which looks like this. So we just have 1 over the eigenvalue minus 1 times, well, the logarithm of the number of images that each of the letters has, but normalized in terms of their frequency, right? These Rj entries are entries of the right eigenvector, so they correspond to frequencies. Right, so this kind of term you're seeing here is quite typical when you're doing entropy calculations. Okay, in good cases, this actually works. These estimates really do give you exactly what you want. So Philip Golka last year, actually I think a couple of years ago, it was only published last year. He had the following theorem. So if our round substitution is compatible, primitive, and if we have this extra condition here, which I'll come to in a second, then the topological entropy really is given by this term that we got just from our estimates. So 1 over lambda minus 1 times this sum of the frequencies times the logarithm of the number of images that each of the letters has under the random substitution. So what's this condition star here? So star is saying for any 2 of our images of a single letter under the round substitution, if you take any high power of the round substitution applied to those words, they never coincide, right? You never get any collisions of this branching process. And that's a problem, right? Because if we don't have that, then actually this estimate that I made earlier, or actually this wasn't an estimate, this was what I said was an equality. Right, the number of words in the image of AI under a high power actually isn't going to be given by this product here, right? Because we're going to be having collisions if they exist. So really all we can say is that this is an inequality. And if we're in the case where this really is a strict inequality, then this term for the topological entropy isn't going to hold anymore. Okay, that's a bit of a bummer if we don't have this this condition here being held. But if we don't have that, well, what about the other extreme? What if we had full collisions, right? So here are the kind of examples that we could have. Here's random period doubling. And here we really do have this condition holding, right? So we have this branching process happening, and we never get any collisions as we iterate our random substitution. So it really is a tree that we're getting. We could be in this example. This is the random Fibonacci substitution again. And here we do have some overlaps, unfortunately, right? So for instance, AB and BA, okay, this A could get mapped to AB and then A, or this B could get mapped to A, and then this A could get mapped to BA. So ABA appears as the image of both AB and BA. So we don't have a tree anymore. We really do have collisions happening in our branching process. But not many, right? You can see that there's just a few collisions that are happening as we go down the tree, or branching process. I shouldn't call it a tree now. Or you could be in this situation where you really have total overlaps, right? Each letter, A and B, both have A, B, and BA as their image. So that means that no matter where you are in your branching process, you can get to everywhere else in the branching process, right? So A, B, and BA have all four of these possibilities in their images. And so really we're having total collisions happening. And these are kind of the extremes, right? You either have a perfect tree or you have full collisions occurring. And so Golka actually showed that these two extremes really give you they give you two ends of an inequality for the topological entropy. So what did Golka say? He said that if our random substitution is primitive and compatible, then we have the following inequality. So here's the upper bound that we had before, right? 1 over lambda minus 1 here. Here's the lower bound that he found, which is just 1 over lambda. So there's not much difference, I guess, 1 over lambda and 1 over lambda minus 1. So this is quite a good bound. But it's important to note that really we can hit either of those bounds. Sorry, here that should be h top, not mu p. Okay, and actually he said a bit more. He said exactly when you get these two extremes happening. So you get an equality for this upper bound if and only if you have this disjoint set condition holding, right? This is the branching tree, the first example, random period doubling. And then you have equality for the lower bound if you have what's called the identical set condition, which is like this example here, right? Identical set in the sense that if you look at the images of these two letters, they have an identical set of images. Okay, and actually you get a bit more because we have this inequality here, and we can also take powers of the round substitution. And the idea is that, well, okay, if you take a power of a primitive compatible substitution, it's also primitive and compatible. So these bounds will also hold for powers of the round substitution. But what's going to change in the bounds? Well, the frequencies of letters isn't going to change. So the RJ entries stay the same. The eigenvalue lambda, well, that's just going to be replaced by lambda to the k as we take the kth power. So we get 1 over lambda to the k minus 1 and 1 over lambda to the k. And then, well, okay, we have to look at a higher power of the substitution here. So this cardinality is going to be replaced by a larger set of words, which is kind of counterbalancing the 1 over lambda to the k. But if you notice 1 over lambda to the k and 1 over lambda to the k minus 1, they're very close. So actually, if you take higher powers of the substitution, this gives you a good way of numerically approximating the entropy. And we've done this in cases where we're in the in-between case, where we don't hit either of these equalities. You can at least take a high power of the substitution, and that gives you a pretty good estimate of the topological entropy. And I should also say that together with Philip Golka, Andrew Mitchell, and Tony Samuel, very recently, we did a similar kind of thing, except instead of looking at the topological entropy, we looked at the measure theoretic entropy. And when you're looking at the measure theoretic entropy, okay, you have to include probabilities for your images. But if you do that, then you get a well-defined notion of measure theoretic entropy. And in fact, we could also find conditions on these probabilities and the substitutions themselves, which give a unique measure of maximal entropy. And this is related to recognizability, but I can't really go into that at the moment. Okay, so what are some examples of applications of this theorem? Well, let's look at the examples that we had before. So if we look at one which really does have this disjoint set condition, so for instance, random period doubling. So random period doubling, unfortunately, is actually not recognizable, but at least does have this disjoint set condition. So the topological entropy is the top end, the upper bound of the inequality. So we can work out the entropy and it's just 2/3 log 2. Unfortunately, because we don't have this recognizability holding, we don't actually know if it has a unique measure of maximal entropy. It could be that it has more than one, but I personally doubt it, but that's still an open problem. The reason that it's not recognizable is actually because random period doubling in its subshift, it has periodic points. That may not be obvious when you first see it, but you quickly see that this word AAB, 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 that is a periodic point inside our subshift. And so by the theorem that I showed earlier, it means recognizability has to fail in this case. Okay, how about the random Fibonacci? So this was one of the in-between cases, right, where we do have some collisions. So for random Fibonacci, we do not have either the disjoint set condition or the identical set condition. We also don't have recognizability. So it's kind of the worst case we could be in. But here we at least can approximate the entropy. So if we write LK to just mean the number of words inside theta to the k, sorry, if you here, so normalized in that sense. Here's the right entries of the right eigenvector, 1 over lambda and 1 over lambda squared, and then the number of images of A and the number of images of B. Then the theorem just tells us that we're bounded above by this term and this term, where 1 over lambda to the k and 1 over lambda to the k minus 1 get arbitrarily close as we iterate. And in fact, you can get a proper formula coming out that the entropy is given by this infinite sum here, which is in some ways kind of mysterious, right? You have both log I appearing in the numerator, and then you also have I appearing as the exponent of lambda on the denominator. But yeah, you can at least approximate that. And so the topological entropy is roughly given by 0.44. But because we don't have either of these conditions, we have no idea as well if this has a unique measure of maximal entropy. And then the last example, I think, for the lower bound. So this is the case where we have total collisions happening. So this is given by the random 2 or more substitution, right? A goes to either A, B, or BA, and B goes to either A, B, or BA. This does have the identical set condition, but quite clearly, I think you could see it's not recognizable because, well, every element of the subshift has multiple pre-images under the random substitution. But because we have the identical set condition, we at least can work out the topological entropy, and it's 1 over 2 log 2 in this case. And it might be interesting to note that even though we don't have recognizability, so we can't use our theorem about measures of maximal entropy, this subshift you can show is actually a coded shift. So all of the elements are just arbitrary concatenations of the word AB and BA. And so that means by various old classical techniques that there is a unique measure of maximal entropy in this case. So even though we don't have recognizability, we do know in this case that we have a unique MME. Okay, are there any questions before I move on to periodicity? Okay. So what about periodicity for random substitutions? Well, so we already know that recognizability at least implies that our subshift is aperiodic. So whenever we do have periodic elements, that means that recognizability has to fail. We also know, at least in the compatible primitive case, that if we have irrational letter frequencies, then that means we also have to be aperiodic. But can we do better? Are there other stronger conditions which imply aperiodicity? So this is a result from last year of myself. So here, unfortunately, we have to restrict just to constant length substitutions. That is substitutions where all of the image words have the same length. But we do get this quite nice condition, I think. So if we have a random substitution, which is primitive and of constant length, actually, we don't need compatible. Satisfying the disjoint set condition, then if every element of our subshift contains some legal word which is not itself an image of a letter under the random substitution, then the subshift is aperiodic. And I should say this condition here, that there is some word which isn't an image of a letter, that's really quite a difficult thing to satisfy. So this theorem is saying that for constant length substitutions, you have to be very special to have periodic points. So here's an example. If we have A goes to AA, BB, A, or AB, AB, A, and B can only go to 5 copies of A, then you'll notice that AA, AA, B, well, that's a length 5 word, and it is neither the image of A under the random substitution or the image of B. And this word appears in every element of our subshift. So by the theorem, that means that this random substitution, its subshift has to be aperiodic. Okay, and then, yeah, if we look at the random period doubling substitution, as I said earlier, we get periodic elements in this case. So if we do get periodic elements, then I suppose the next question one would want to ask is, how many are there, right? How many periodic elements are in the subshift, say, of a particular period P? So we can answer that. From the same paper this was, if we have a random substitution, which again has to satisfy the disjoint set condition, then we do know that there is a decidable procedure, and in fact, it's an algorithm that I gave, to check if any particular word U is a periodic block for our subshift. So that means that we can get a computer to check words to see if they're periodic blocks, and then we can just count how many words of any particular length there are which are periodic. So with random period doubling, we get these values for the number of periodic elements in our subshift. I would be very interested if someone could tell me any patterns they spot in this table, because to me, it's quite difficult to really see anything going on here. So I'll just say that the columns here, P is the period of one of our elements. This is just the number of, the number of elements which have that period. Just period, not prime period. So for instance, length 6 would also include the elements of length 3 here. And then orb P is the number of distinct orbits of any particular period, right? So this is saying there are 2 orbits of exactly length 6. Okay, I think that table's on the next slide. Yeah. So like I said, I do not understand this table. I don't get what's going on here. In some sense, it's very mysterious. There are a few things that you might be able to spot. So here are some questions that I have. So my first question is, if we have a period which is a multiple of 3, you'll notice that these are all multiples of 3 here. Then is it true that there is a word with prime period P? So is it true that every multiple of every multiple of 3 admits a periodic element of that period, prime period? The other thing to notice is that you sometimes get these large numbers appearing in this column. For instance, with 36, you jump to 19 million for some reason, and then 42 as well, you jump to 13 million. it looks like the number of powers of 2 of our prime period, of our period P determines if the number of periodic elements of that period is going to be large or not, right? So if we have, for instance, 33 has very few factors of 2, so it kind of has a drop down from 30 to 33 here. So okay, we can at least spot a pattern like that seems to be happening, but how do we formalize this? Is there, I guess, some kind of like Euler formula that is happening here? And then, okay, in terms of the topological entropy, it's normally a good idea when you have periodic points to, again, look at their exponential growth rate, the number of them. And it is actually true in this case that if you do have periodic points, then the exponential growth rate does give you the topological entropy. But how about if we just look along this sequence of powers of 2 times 3? Is it still true that the topological entropy is given by this limit here? I maybe should have put lim sup here because it's not known if this limit even exists. Okay, let's maybe move on from periodicity to some other open questions I have. I should say I'm getting to the end here. I think this is the last slide. So some other questions I have: is the topological entropy of random Fibonacci actually the logarithm of an irrational number? So is this sum here the logarithm of an irrational? We still, I think, do not have any examples where we can prove that the entropy is not a logarithm of an irrational. If we go back to the examples that we had, you'll see here, for instance, we have a half log 2, 2/3 log 2. What about this? Is this some rational number times logarithm of a rational, or is it really something a bit more irrational? We haven't looked at all yet at palindromic complexity and the entropy that you would get from looking at the exponential growth rate of just palindromes. Can we fully classify the periodic points? Oh, sorry, when we have no periodic points? So can we get a version of Mosse's theorem for random substitutions? Can we enumerate the number of points of any particular period P without this disjoint set condition that I needed for this theorem here? Just maybe a random thing to ask. Power free properties, what can we say for just an arbitrary random substitution? Does the random period doubling substitution have 5th powers? I don't know. Actually, no, I think it does have 5th powers. Does it have 7th powers? And then maybe more on the dynamic side of things, what kinds of subshifts can we get appearing as random substitution subshifts? Where do they kind of fit in the hierarchy of, shifts of finite type, suffix shifts, coded shifts? Are they more towards that end of the hierarchy, or are they closer to the deterministic setting where we have this long range order appearing? So actually, we do know, for instance, that all mixing shifts of finite type do appear as random substitution subshifts. This was work with Philip Golke and Timo Spindler. But what about suffix shifts? We have no idea about suffix shifts. And then essentially nothing has been done in higher dimensions. So what about random substitutions or random block substitutions in Z2 or higher dimensions? Or how about random substitutions on tilings? Obviously, you can perfectly well define a compatible primitive Penrose substitution. So what are some properties of those Penrose tilings that you get out, or random Penrose tilings that you get out? Yeah, and I should have put a thank you slide, but I didn't, so I'll stop there.
Thanks, Dan. Does anyone have any questions for Dan? I don't hear any questions. I don't have a question myself, but I'll just say that I found that quite interesting because in my work, I often have to use one of these random substitutions to prove that there are exponentially many words avoiding such and such power. So seeing those exponential growth calculations, that was quite interesting for me.
Okay, can I ask, what do you call them? Because you probably don't call them random substitutions, right?
No, I call them multi-valued substitutions.
Right.
But that may be a non-standard word. I think in the very old L systems literature, these would also maybe be called just 0L systems.
Yeah. Well, when we were coming up with the term, because somehow, at least from the dynamics point of view, these have not been well studied in the past, and I come from the topological dynamics side of things, so we didn't know what to call them, and it was only after we wrote our paper that we realized actually they appear in other places, and people have looked at them. Maybe they've looked at different questions, but normally they're not called random substitutions. And 0L systems, like you mentioned, were one of the ways that they're brought up.
Right. It looks like Melody has a question in the chat. Can you see it, or should I read it?
Maybe you could read it out.
Sure. Is there any difference between random substitutions and S-adic systems whose substitutions have the same incidence matrix?
Right. Yeah, that's a good question. And I think it's easy to get confused when you know what S-adic systems are, to see this and think that it's similar. Unfortunately, they're really quite different. So because at every application of a random substitution, we're independently choosing on each letter potentially a different image, it means that we're quite far away from the S-adic case. For S-adic systems, you're applying the same image to each of your letters for any particular iteration. It's just that as you move from one iteration to the next, you may change the substitution that you're applying. Here, it's even more choice. Thanks, Melody.
Dan, if you
Hi,
take one of your random subshift, the big one, and can you take some kind of quotient there, and then what you get is the subshift you will get by choosing a particular process
realization
of probabilities or
yeah, I don't know about a quotient, but maybe the question you're kind of trying to ask is there like a shift sort of living perpendicular to this, right? Because we have choices for each of our images, so you could code the choices of each of the A's as you go down, and you get some sequence of zeros and ones. So is there a full shift living in there? And in some sense that is there. It's just it's not quite as simple as saying it's, you know, a topological factor of our system or something like that. I don't really know how to formalize it. But you're right, something like that is living in there. It's just a bit complicated.
Okay, thank you, Dan.
Does anyone else have a question? Well, if not, thank you, Dan, for your talk. Thank you to everyone for coming today. In 2 weeks, we'll have our day of short talks. I think we have